Okay, sublimation. Here's an illustration of frozen water, ice. And the ice particles are not still. They are moving, right? Vibrating. Some of those molecules, not very many, but a few of them have enough energy to break loose and go directly from being in that solid to a gas. Because even though the ice is cold, there's an average kinetic energy related to the temperature, but there's a few particles that have very high energy. And so those can escape. This process of going from a solid to a gas, skipping the liquid, is called sublimation. The opposite, going from a gas directly to a solid, is called deposition. So this is a solid, and yet it will also have a vapor pressure. The vapor pressure is going to be much lower than the vapor pressure for a liquid, but it does have a vapor pressure. Any questions? Here's a picture of dry ice. Dry ice is solid carbon dioxide, frozen carbon dioxide. When you take it out of its cold environment where it was stored, it begins to sublime. It doesn't melt. You can't have liquid CO2 at atmospheric pressure. It sublimes, goes directly to the gas state. Now what you see, it looks like there's like vapor or fumes coming off of this. What you're seeing is the cold air, and as the air becomes cold, the water that's in the air condenses and forms like a cloud. It's called dry ice because it doesn't get things wet, right? You ever been on a picnic and you had some sandwiches in the cooler with ice? And you get to your picnic and the ice has melted and there was a hole in your sandwich bag and everything's wet and nasty, right? Dry ice won't do that. Regular ice does sublime, but not as fast and not as usefully as carbon dioxide does. But this will explain some things that happen in your freezer. So if you've ever found maybe a forgotten ice cube tray or some ice cubes that got stuck in the back of the ice cube maker, and they're a lot smaller than the other ice cubes. They weren't originally that small. They've been subliming slowly as they've been forgotten in the back of the refrigerator, the freezer. So they will sublime. Ice crystals will grow inside of bags of frozen food. This happens like with French fries or tater tots, you know. It's been in the freezer for a while and you're like, oh, great, I'm gonna have some tater tots. And you open the bag and you dump them on the pan and there's the tater tots and there's a bunch of ice crystals. I mean, who puts ice crystals in a bag of frozen tater tots, right? It's gonna get them wet and then they're gonna be all soggy, right? You gotta get rid of the crystals there. Those water crystals, ice crystals, came from water that was originally in the tater tots. It sublimed. It couldn't go anywhere because it was in a bag, and so crystals grew inside the bag outside of the tater tots. Food gets freezer burned. You leave a nice steak in the freezer too long, and it gets all dry and nasty on the outside, and we call that freezer burn. It's not that it got hot. It's dehydrated. Because again, the water molecules that were in the frozen food sublime and escape. So there's two things you can do to prevent that or reduce that. One is to use a deep freeze. And a deep freeze is a freezer that's colder than a regular freezer. The colder the freezer is, the less sublimation will occur. Or you can seal the food in something like a vacuum seal bag, or cover it very tightly in foil and then with plastic. Anything you can do to reduce the airspace around the food will help to prevent freezer burn because it doesn't give the water vapor anywhere to go. Any questions? Sublimation in your kitchen. Okay, now we'll turn to the liquid-solid transition. So you take a block of ice and begin to warm it up. The average kinetic energy of the molecules increases, the molecules vibrate faster. When it gets to the melting point, so here we have the temperature over here, the temperature going up. When it gets to the melting point, now those molecules have enough thermal energy to overcome partially the intermolecular forces that are holding them together. They're not escaping into the gas state, but they're able to slide around relative to each other. And so we have melting. At the melting point, as heat is added, you don't have an increase in temperature. This is a lot like what happens in the gas-liquid transition. Additional heating just causes the substance to melt faster. The temperature doesn't go up until all of the solid has melted. So anytime you have ice and water mixed together, like in my rock star that's rapidly disappearing, the temperature in there is going to be really close to 0 degrees Celsius because the water is in the process of melting. And anytime you have water and ice in equilibrium, the temperature is going to be 0 degrees Celsius or very close to it. Any questions? So melting is an endothermic process. That makes sense to us. How do you get an ice cube to melt? You put energy into it. How do you get chocolate chips to melt? You put them in a pan and you heat them, right? So we call this the heat of fusion. Fusion is another word for melting. And that's one that doesn't necessarily come to mind, like vaporization makes a little more sense. Fusing, I think of the chocolate chips, and when you melt them, when they become a liquid, they fuse together into one thing, right? So fusion is melting. Heat of fusion, heat required to melt 1 mole of a solid. So for water, the heat of fusion is 6.02 kilojoules per mole. And this is always going to be a positive number as well. So melting is endothermic. That means that freezing is exothermic. If I take a mole of water and I freeze it, that's going to release 6.02 kilojoules of energy per mole. That's not obvious. But the way your freezer works is it has essentially a heat pump that is pumping heat out of the inside of the refrigerator. Where's the heat coming from? It's coming from the food freezing. Once the food has frozen and becomes the same temperature as the inside of the freezer, then there's no more heat to pump out other than what leaks in through the imperfect insulation. This idea that freezing is exothermic actually has a lot of significance for the Central Valley. As you may know, south of here where I live, they grow a lot of citrus trees. Oranges, lemons, grapefruits. In the winter, when the oranges are on the trees, the temperature sometimes drops below freezing. So then what happens to the oranges? Well, if it stays too cold for too long, the oranges will freeze. And if you've ever seen like a head of lettuce or something that got stuck in a part of the refrigerator that was too cold and it froze, when you freeze fruits and vegetables, a lot of times they'll get really mushy and nasty, right? Freezing oranges is not a good idea. So how do you keep the oranges warm? You have this big field. You don't need to warm it up very much. The temperature doesn't usually drop much below about 26 degrees Fahrenheit. And you just need to keep it above that. It has to get below about 26 for 4 hours or so to damage the oranges. So we don't need much of a nudge in temperature. What the farmers do is they will flood irrigate the fields so that the ground is very wet, sometimes even standing water. Then what happens is the temperature drops during the night, the water begins to freeze. If you look at this graph, now what we're doing is we're going the other way. So the air temperature is going down. When the water begins to freeze, it remains at the same temperature. It's actually giving off heat to stay at the same temperature. So where that water is freezing, the air is 32 degrees Fahrenheit. And then they have wind machines that help to blow that air around, and most of the time they can keep the citrus crop from freezing. Any questions? So the heat of fusion is a lot less than the heat of vaporization. Here's a bar graph showing you the comparison. Heat of fusion in blue, heat of vaporization in the bright pink. So for water, the heat of fusion is around 6 kilojoules per mole. The heat of vaporization is 40 kilojoules per mole. The reason for this is that in melting, you only have to partially overcome the intermolecular forces so that the molecules can slide around. In vaporization, you have to completely break them so that they can separate in the gas state. Here's a table from your textbook with melting points and heats of fusion for several different substances. And again, you don't memorize these, you'd look them up in a table. But sometimes they'll give you a homework problem and they won't tell you what the heat of fusion is, and you have to go look it up.